All right, cool. So looking around, looks like we had some success on the warm-up, and then other spots where we were not sure, and that's kind of the idea. Because we got to start with where we're at, go to where we can go no further, and that's where we add more information so we can keep going, right? We got to identify that spot. Where's that spot where we can't keep going, okay? So we're going to talk about a problem we can do, a problem we can't do. And the difference between the two problems is one of them is a kind problem, meaning like it's nice, like the teacher made it so it would work out kind of nice, right? And then the other one is not so nice, right? So what do I mean by that? Well, let's start here. Okay, so we know that we have to find x, the x value that makes this true, right? Essentially, you have a couple different options here. You always have the option of guess and check, but we also learned a process, right? We learned that, well, if we want to start to get the thing with x by itself before we can do anything, right? The thing with x is 5. It's 5 to the x, right? To get that by itself, I need to do what? What do I need to get rid of? The 2. So I have to divide because it's multiplying. So I would divide by 2, divide by 2. I get 5 to the x equals 25. Now this problem is super kind because this is actually such a common situation that you might already know the answer, right? 5 to the x is 25. What must x be? 2, right? Because you know 5 squared is 25. You've seen that a million times, right? But what we've talked about is that we develop processes and strategies with simpler problems so that when we get to harder problems that aren't so obvious, we have a method, right? So we learned a process for getting to an answer that isn't just guess and check or I know what makes this true, right? And that process was, well, let me rewrite the 25 as in a different form, and then maybe it'll reveal itself. So we'll pretend we don't know it's 2, right? And I say to myself, well, I know there's a rule about common bases. So maybe if I rewrite this as 5 to the something, I can get this to a place where I can solve it. And I say, well, 25 is 5 to the 2. So I say, okay, 5 to the x equals 5 to the 2. And then I remember my rules for common bases, which say if you have the same base and you have an equal sign, well, then the exponents must be what? Equal. They have to be. If this can't be 3, that wouldn't be true, right? The equal sign says things are true, right? 5 to the 3rd is not 5 squared, right? 5 to the 4th, 5 to the negative 1, none of that would be true. 5, the only thing that would make this true is 2, so we say, therefore, x equals 2, right? We know it must be true. So that's like a super kind problem. Then there's a little bit less of a kind problem where you were like, I don't know, 3 to the x equals 243. And it's not as easy as 5 squared is 25 that you know by heart. You might not know what that is. But it's still kind in that you can get there, right? Because you pick up your calculator, you start going, I don't know, 3 to the 3rd. No, 3 to the 4th, 3 to the 5th. I don't know, 3 to the 5th? Yeah, 3 to the 5th. So 3 to the x equals 3 to the 5th. Took a little bit more thinking and trial and error, but we still got there. We know x equals 5, right? And then you could also have like x squared and something else. But it doesn't really matter what is here and here, because as soon as we see these common bases, we just set these equal to each other, right? They can be crazy here and crazy here, but we make a new equation and we solve that. This was already solved, so we're good. Okay? Kind, right? Because it's a base 5 or a base 3. We got there, right? Now let's look at a less kind problem. Well, it looks very similar, so we're going to start with the same step. I'm going to divide by 2, and I get 5 to the x equals 20. So I think, well, the teacher said if you write them as 5 to the and 5 to the, then you'll be in good shape. However, what's 5 to the 1?
5.
What's 5 to the 2?
25.
25, and we just passed our number, right? So we have an issue here. We can't write this as 5 to the something. So we need a strategy. We need somewhere to go, okay? And that's what today will be about, is what can we do when we have this situation and we don't have a method, okay? So that's where we're going. Now, there is an interesting thought process you could do here to try to narrow down what that x might be. If you're in the x that makes it true mode, anybody have a guess of what x might be?
No.
Well, I mean, we know it would have to be between 1 and 2.
Mm-hmm. So pause there. Does everybody see that, right? 5 to the 1 is 5. 5 to the 2 is 25. 20 is between those two numbers. So the exponent that we're looking for has to be between 1 and 2. Keep going. Okay. So let's think decimals, because that's I think easier, right? So you might say, well, I know it's between 1 and 2, right? So I'll try 5 to the something between 1 and 2. Is it closer to 5 or 25? 25. So I probably won't start in the middle. I'll probably start at 1 point, what do we think? 8? Okay, 1.8. And I put that in my calculator, and what do I get? 18 point what? 1. Okay, so have I gone high enough? Okay, then I go 5 to the 1.9. And what do I get? 21. Okay, so then I know it's between these. How do you go between these? Yeah.
I got to 5 or to 1.8613, but that's not it yet.
Okay, so 5.186 is about 20. Notice I didn't put equal, right? But what if we wanted equal? We still need another method. What if we wanted to know that exact number, right? So that's what today will be about. Okay, now the other thing I want you to see today before we get into the lesson is the relationship between inverse functions. Now, I put this in the you can do already section, but to be fair to you, we haven't done this in this class. This is a previous thing. Does anybody remember inverses? Okay, that's okay. I will recap. Okay, a little crash course in inverses. So, what's an inverse operation?
Opposite.
An opposite operation. So an inverse function is a opposite function, right? So we want the opposite of this. Right? Okay. We'll come back to doing it algebraically. Let's just look at the graph for now. Okay? If we're looking at this function and we're trying to be we're thinking about its opposite, let's just analyze it a little bit, some of its points, right? So I got 0, 0. This point is 1, 2. This point is 2, 4. This point is -1, -2. And this point is -2, -4. So that's a function we're dealing with. And we're looking for its inverse function, its opposite function. Okay. So the opposite of 2, 4 is not negative. You might think so. What's the opposite of 2, 4?
4, 2.
4, 2, right? So the opposite of 2, 4 is 4, 2. The opposite of 1, 2 is 2, 1. The opposite of 0, 0 is just 0, 0. The opposite of -1, -2 is -2, -1. This would be -4, -2. And what does that form? What do all these points form? Another line, right? And this is the opposite of the first line, okay? And what you will find is that inverse functions always reflect over the diagonal, the y equals x line. They always flip over that. You don't need to remember all this. This is just a little crash course in inverses. Okay, So this is its own line, right? We could actually find it. It's actually y equals 1/2 x because it goes over up 1 over 2. It's got a b of 0, okay? But what if we didn't have a graph? There's a way we could find it, right? And this is not the lesson, just a little crash course in inverses. Okay, so we want the opposite of y equals 2x, and we want to find it without a graph. Well, what do we do to all those points? We flipped something. The x and the y, right? So what should we do? No, we don't need to do that. We're going to use algebra. What would happen if I flipped this x and y? What would it look like? X equals 2y. Well, we like functions that are y equals, right? So I'm going to divide by 2, divide by 2. I get y equals x divided by 2, which can be rewritten as y equals 1/2 times x, which is exactly what we found when we graphed it, right? Now, what's the point of all this? Well, if you know this, you could always find this, right? You could always find your opposite because you just have to flip everything, right? And that means they have a relationship. Inverses have relationships, and you can use one to find the other. Okay? So maybe that'll help us, because when we have x in the exponent, it's causing us issues. What if we found our inverse? So we go over here and we say, well, what if we did it over here? Maybe it'll help us. Just knowing relationships helps us, right? So I flip them and I get x equals 2 to the y. But I run into the same issue where I have a variable and an exponent. I don't know how to get it out, right? Well, let's look at the graph. Maybe we can use the graph. Look at some points. I got 0, 1. I got 1, 2. I got 2, 4. And 3, 8. And for good measure, let's do a -1. So that's -1 and then 1/2. Okay, so if we flip all these, let's at least see what this inverse will look like. The opposite of 3, 8 is 8, 3. That's off the graph. The opposite of 2, 4 is 4, 2. Opposite of 1, 2 is 2, 1. 0, 1. 1, 0. -1, 1/2. 1/2, -1. And then I guess it would just do this, right? So this is what the inverse of an exponential function looks like, right? Because this is exponential, and this was the inverse. And they are inverses of each other, by the way. Now, we have a name for the blue one. We should have a name for the red one. Anybody have a guess what that name might be? Well, they are inverses, but they have their own names too. It's not exponential, right? Doesn't behave exponentially. It kind of is like the opposite. It flipped over that diagonal line. Give you a hint. Look at the top of your page today. This is a logarithm. Okay? So that's an exponential function. That's a logarithmic function. Okay? Logarithmic. Okay? And that is how we're going to find that missing piece. So these have a relationship. Therefore, if you know this one, you could find this one. If you know this one, you could find this one. And that will help us because we can change some forms and get the x or the y or the whatever out of the exponent, okay? So let's just kind of summarize the point of all that because it was kind of an exploring thing. What is the summary of our challenge? Well, think back to 5 to the x equals 20. What was the problem there? Where was our variable? In the exponent, and we don't have a way to solve for that. So our challenge is we need to solve for variables in the exponent. Like 3 to the x equals 15, something like that, right? We don't know how to do that. We need a way, right? And our extra challenge is, how do we get the x out of the exponent? Because it's a problem right now. How do we get it out? Well, if we know the inverse of this, we can get it out, okay? So our solution to our challenge, to our problem, is what? The inverse, which the inverse of an exponential function is? A log. We just say logs for short. Rarely do I say logarithmic, okay? So logs. Logs are our answer to our problems. Now, I will say, the logarithms, for some reason, I think I know the reason, are like confusing and scary for students, and it's only because they're new. It's brand new. It's like, never seen this before. Most stuff in here is building on previous stuff, and you're like, I'm not going to understand this, right? They're actually not that complicated. They have all the same pieces that you worked with before. They're just written differently. So try to stay open-minded. Don't overwhelm yourself. Question? Yeah. So don't overwhelm yourself. Don't just be like, okay, open-minded. Let me learn about this, right? Today we're just learning about them and converting between the two forms, and that's it. Okay. All right. So let's talk about logs. Logs. Logarithms, logs are just another way to represent exponential relationships. Okay? It's just a different way to do that. So before we go to the logs, let's talk about the way we know already, so how do we talk about exponential relationships already? The exponential form that we've been using, well, every exponent that we've ever had has a base, an exponent, and then it has a answer, right? And these letters I'm just using to be friendly. Like, you might see other different ways of written this, but you got your base, you got your E, which is your exponent, and you got your A, which is your answer, right? I don't know why I flipped that order. Okay, so that's how we are used to doing this. So for instance, you might have 6 squared equals 36, right? Base, exponent, answer, right? That's how we write them normally, okay? But we talked about, well, what if this is an x and this isn't so friendly? We got to get it out. So what we do is we convert it to its other form, which is logarithmic. And it's got all the same pieces, okay? This is our exponential. And then our logarithmic, we would say log. And then, do you know how exponents are like up top? We call that superscript. Logs, it's the opposite. We have a number that's down low, like lower than the numbers. That's called subscript. So what we do is we put the base down there. Then we say answer. And that equals the exponent. So again, the same 3 pieces, base, answer, exponent, but just in a different form, okay, with this log thing. And log, by the way, is a button on your calculator that we'll get to. Okay, so that's why it's helpful. Subscript, you just halfway down. So just have it like hanging off the last letter. Oh, on your calculator? We're not getting to the calculator yet. Okay, so that is our situation. Now, a key thing to keep in mind here is, well, what was the point of all this? Well, the log is the exponent. Okay, and I'm going to say that a lot. The log is the exponent. What do I mean is? The log is the exponent. I'm using that word is in a math sense. What? It's equal. Is equal, right? So when we say is, we mean equal. And look, the log is the exponent, right? So if you're trying to find an exponent, use a log because it is the exponent, right? Its answer, not that answer, its answer is the exponent. So it really helps us when we have a missing exponent, when we have an unknown exponent, right? We use a log and suddenly it's by itself on one side of the equation, okay? All right, so all we're doing today is practicing converting between forms, so we'll do that a little bit, okay? So I'll do a couple, you'll do a couple, then we will find some missing pieces and we'll be done. Okay, so the exponent form, an example that we know, we got something like 9 equals 3 squared, right? So this 9 is our what? Careful. I wrote it backwards on purpose. It's not always on the left or right, right? Answer. Our 3 is our base. By the way, that's happened 3 times today. And so don't feel bad. And this 2 is our exponent. Okay, so now we want to write this as a log. And by the way, you after today, I would want you to be able to go back and forth between these, like one to the other, okay? So our log, well, we would say we have log, and then we need to put something here, and then equals something here, right? And we talked about those pieces, right? What goes at the bottom? The base, which is 3. What color was it? 3. What goes next? 9. And what goes on the other side of the equation? 2, because the log is the exponent. It equals the exponent, okay? Now, what if you went the other way? What if you were like, okay, I have log 2, 16 equals 4. Well, now you would say, okay, I need a base to an exponent equals an answer. What's in the base spot over there? 2. What's in the exponent position? 4. And what's in the answer position? 16. 2 to the 4th is 16. Question?
What's funny is that 4 to the 2 is also 16.
It is a special case. Yep, that is true. Okay, so I'm going to give you 2 of them for you to do. Okay? So here we go. Log of 381 equals 4, and 10 to the 3rd equals 1,000. Let's go ahead and put those, convert those to their other form. All right, so again, we're just looking for the 3 pieces and then putting them in the right spots. What's my base over there? What's my exponent? Equals my answer, 81. And you sense check. Yeah, that's true, right? Over here, what is my, so I write log, what's my base? 10. What's my answer? 1,000. Equals my exponent, 3. Okay, special case, ready? This can be rewritten as just log 1,000 equals 3. Don't pack up. We're going to the end. Okay, so log 1,000 equals 3. What's missing here?
10.
The 10. That's because log of 10 is so common that you can just get rid of the 10. You just write log, and everyone knows it's just base 10, right? That's what your calculator speaks in, log 10. So if you did log 1,000 in your calculator, enter, it will tell you 3. It's assuming 10, okay? And we'll talk more about that. Log of 1,000. You don't have to do the base. Okay, 3 practice problems and then we're done. We're going to convert to solve. So, here we go. First one. Log base 3, 27 equals x. Second one, log base 2, x equals 5. Third one, log base x, 16 equals 2. Now, for each of these, well, we just started working with logs. Might as well turn them into exponents, and then we'll know how to solve them, okay? So here's what we're going to do in each of these cases. And you'll notice that the x is in a different spot each time, because I need you to be able to do each situation. What if the x is the base? What if the x is the exponent? What if the x is the answer? Okay? So you're converting each of these to that exponent form, and then you're solving. Ignore that. Okay. Okay, we're short on time, so I'm just going to roll here. This would be base 3 to the x equals 27. Well, that's 3 to the x equals 3 to the 3, x equals 3, right? This one would be 2 to the 5th equals x. Well, we know we can do 2 to the 5th, that's 32. So 32 equals x. This one would be x to the 2 equals 16. If x squared equals 16, then
4.
x equals 4. So that's what you'll see on your homework.